topic 8, current electricity, in the Regents Physics curriculum. This section, 8.2, is called current. Now, to distinguish the previous topic, electrostatics, from current electricity, I'd like to say that in electrostatics, the electrons pretty much did what they wanted to do. In current electricity, we kind of tame the electrons. We force them to move through wires so that we can hook them up to the refrigerator or have them run through our automobile engine in a certain way so that the electrons can do work for us, so that we can harness the electricity to power devices. Right? So we can think of electrostatics as kind of wild electrons doing whatever they want to do. In current electricity, the electrons, we're forcing them to flow through wires so that we can tame them to do useful work for us by powering our electrical devices. Now, current is represented by the capital letter I. That's the symbol for current. Charge is represented by a lowercase q, and time, you know, is represented by a lowercase t. The definition of current. Current is defined as the amount of charge. You know that electrons carry negative charge. Right? So current is defined as the amount of charge which flows past a given point in a certain amount of time. I copy this down, and I'm going to draw a picture of an electrical device so that I can show you where current generally flows. So what are we going to be talking about in the current electricity topic? Well, here's a microwave oven. I'm going to call the microwave oven a device. A device could be a microwave oven, a light bulb, a refrigerator, the engine of a car, devices that use electricity in particular. Now, we know that the electricity comes through the wire, right? We plug it into the wall, the electricity comes through the wire, and you probably know that inside the microwave oven, inside the refrigerator, inside the light bulb, there are more wires that you can't see. Well, the electricity is flowing through the wires so that we can harness that electricity to do work, the kind of work that we want it to do, right? We want this particular electricity to cook our food for us. In a refrigerator, we're powering motors and condensers and such so that we can keep the food cold, right? In a car, we want the headlights to come on, we want the wheels to turn, etc., etc., etc. All right, now, inside the device, there are smaller devices called components, and we will be talking a lot about resistors, not so much about capacitors, but these are all little parts, little devices inside of the microwave, right? And we call those components, and the electricity also flows through those components for various reasons. All right, so again, the electricity is coming through wires in the current electricity topic. And we said in the definition of current that if we pick a point, all right, I'm going to pick this point right here, all right, maybe we'll put it with an arrow, all right, pick this point right here, and I would like to figure out the current, how much charge, all right, let me redraw my little wire here, all right, I want to figure out how much charge flows past this point in, let's say, 1 second, in a certain amount of time, all right, so current, all right, capital I, is the amount of charge per time that flows past a certain point. Pick any point you want, and we want to see how much charge flows past. Now, we know that the charge is being carried by electrons. Now, one of the things that sometimes makes math or chemistry or physics kind of difficult is that you can't always make a picture or a drawing of everything that you learn in physics or chemistry or math, right? I mean, we try really hard. So it would be very, very difficult to have a picture of charge flowing through a wire. But then again, on the other hand, since charge is being carried by electrons, it's very, very easy to picture electrons. We might picture electrons as little dots. Okay, so here's some electrons. So we can easily picture the electrons flowing through the wire, right? Whereas it's not quite as easy to picture charge flowing through the wire. Now, the question becomes, well, what exactly will we say that one of these dots represents? Is one of these dots going to represent one electron? Does that make any sense? Well, an amount of charge that we often use very comfortably, right, in the first year of physics, all right, and in all of physics, all right, is 1 coulomb. All right, 1 coulomb is a nice, handy amount of charge, and we use 1 coulomb or 5 coulombs or half a coulomb or even microcoulombs, right, quite often. Now, the thing is, 1 coulomb, well, how many electrons is that? All right, so I'm going to convert the 1 coulomb to electrons. All right, so I want to get rid of coulombs, so I'm going to put coulombs on the bottom so I get rid of coulombs, and I want electrons, all right, on the top here. Well, 1 electron, we know from the front of your reference tables, has a charge of negative 1.6 times 10 to the negative 19 coulombs. All right, and we'll make this negative because it's electrons. Okay, so I can use this to convert coulombs to electrons. So I will know 1 coulomb, well, how many electrons is that? The coulombs are going to cancel. Right? I pick up my handy calculator. I say 1 divided by, see how it's on the bottom? The equal sign is over here. Don't cross multiply, you can't. All right? This is 1 divided by this big number down here. Well, actually, this is a very small number. 1 divided by this number, okay? So 1 divided by 1.6 times 10 to the negative 19 is, wow, 6.25 times 10 to the 18th electrons. Wow, that is a big number. 1 coulomb is a lot of electrons. Let's see how big that number really is. All right, 6.25 times 10 to the 18th. 625, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, thousand, million, billion, trillion, quadrillion, quintillion, thousand, million, billion, trillion, quadrillion, quintillion. All right, 6.25 quintillion electrons. That's a lot of electrons. All right, so what I am going to do throughout the current electricity topic is I am going to use one of these dots to represent this many electrons. I am going to use a dot to represent 1 coulomb of electrons. All right, so that's 2 coulombs, and that's 3 coulombs, 4 coulombs, 5 coulombs, 6 coulombs, 7 coulombs, because it doesn't make any sense for this to represent 1 electron. We couldn't possibly do anything in physics with 7 electrons, 3, 4, 5, 6, 7. But 7 coulombs of electrons, we might be able to power some electrical devices with that. All right, so I'm going to use a dot to represent 1 coulomb of electrons. So there's 1 coulomb, there's another coulomb, right, there's another coulomb. Right, so right there I have, for example, 3 coulombs of electrons, and that 3 coulombs of charge, which represents 3 times this many electrons. So this is my little convention here. All right, each little black dot is going to represent 1 coulomb of electrons. That's 6.25 times 10 to the 18th electrons. And since you now can have a picture in your mind of the charge flowing through the wires, it's going to be a lot easier for you to understand, for example, the difference between current and voltage, and perhaps some of the other words that we're going to be defining and using in this topic. So we're going to jump right into drawing your very first, very simple circuit. A circuit would be wires and resistors, different components that are inside of the devices that we use, right? Inside the microwave oven, inside the refrigerator. There are tiny, tiny little circuits imprinted on circuit boards, right? And chips inside of computers. So you need to know how to draw the symbols for the various components of various circuits. All right, let's start with a cell. All right, a cell, basically cells make up batteries. To draw a single cell, you would draw a negative and a positive. That would be a cell. Now, as soon as you put two or more cells together, we call it a battery. So putting two cells together, all right, a negative, a positive, a negative, and a positive, that's the drawing that represents a battery. So this drawing represents a cell. This drawing represents a battery. Wires are just drawn as lines. So a wire would be a line. It might be going across, it might be going up and down, doesn't really matter. And finally, a resistor is drawn as a series of zigzags. 1, 2, 3, something like that. That's plenty. You could draw a couple more zigzags. You probably wouldn't want to draw too many fewer, but a couple more, 1 or 2 more zigzags, no problem. All right? So you have to learn how to draw a cell, a battery, all right, which is 2 or more cells put together. All right? A wire is just a line, all right, and a resistor. All right? Pause the video, copy down these circuit symbols. We'll use them in just a minute. All right, we're going to draw our very first circuit. We're going to draw what's called a series circuit. All right, a series circuit with 1 battery and 2 resistors. Now, if you remember, we said that a battery would look like this. There would be 1 cell and maybe another cell. All right, so that's 2 cells making up a battery. All right, I'm going to draw some wire, okay? And I'm going to draw 1 resistor here, all right, and I'll put another resistor over here. Okay, it doesn't matter how many zigzags you make, not a big deal. All right, so this is a series circuit. There's a battery, there's the wire, that's a resistor, another wire, a resistor, and another wire going back to the battery. Now, this circuit is going to have a current of 6 coulombs per second. So I'm going to take 6 coulombs. All right, 1, 2, 3, 4, 5, 6. All right, they're coming out of the battery. All right, and here they go. All right, 1, 2, 3, 4, 5, 6. And what I want you to look at, the only thing I want you to get out of this, because I'm not going to get really, really complicated with the circuit right now. I want you to see the current, all right, 6 coulombs, going through this resistor. All right, these 6 coulombs, they're actually riding on the wire, but if I ride them right on the wire, they're going to erase all my lines, and I really don't want to do that. All right, so the 6 coulombs, all right, go through this resistor. All right, 1, 2, 3, 4, 5, 6. So all 6 coulombs go through this resistor, and then 6 coulombs also go through this resistor. All right, so if I were to put my finger here and say how many coulombs went by in 1 second, all right, I would say 6. And how many coulombs went by in 1 second? I would say 6. 1, 2, 3, 4, 5, 6. All right, with a series circuit, there is no way for a different current to go through any of the components. Whatever coulombs go through this resistor have to go through that resistor. So keep in mind that in a series circuit, right, all the currents are the same. The current going through the battery is 6 coulombs per second. The current going through each of the components, in this case 2 resistors, is 1, 2, 3, 4, 5, 6 coulombs per second. The current going through this resistor is 6 coulombs per second. All right, in a series circuit, all of the currents are going to be the same. And so now we're going to draw a parallel circuit. A parallel circuit with 1 battery and 2 resistors. You'll see that it's going to look different from the series circuit. The current out of the battery, the current going through the battery, is still going to be 6 coulombs per second. But you'll see that the current going through each of the resistors does not, well, certainly isn't going to be 6, and does not have to be even the same. All right, so let's start drawing. We're going to draw a battery. All right, so here's a cell. If I put at least 2 cells, I have a battery. So here's the battery, all right, and here's the wire coming out of the battery, and I'm going to draw 1 resistor here, and since this is a parallel circuit, I'm going to draw the other resistor over here, okay? And what I'm going to do now is show you the 6 coulombs, all right, coming out of the battery in 1 second, all right, 6 coulombs each second. So the 6 coulombs come out of the battery, so the current out of the battery is 6 coulombs, and that takes 1 second for them to get out. They're pretty quick. Now, when the coulombs get to here, they have the choice of either going to this resistor, right, or going to this resistor. Now, it could be, we're not going to go into the details about why they split up in a certain way in this video. We'll do that in another video. But it could go 3 and 3. All right, it could split up that way. Or it could go, 2 of them go this way and 4 of them go this way. Or perhaps 2 of them come this way and 4 of them go that way. Right? It could be 1.5 coulombs go this way and 4.5 coulombs go the other way. In any case, these 2 currents are going to add up to the total 6 coulombs, all right, per second. Now, just for argument's sake, let's have 4 of them go this way. All right, so 4 coulombs per second are going to go through this resistor, and 2 coulombs per second are going to go through this resistor. All right, so you see right away in a parallel circuit, the currents through each of the components, the light bulbs, the resistors, the capacitors, whatever, don't have to be the same. All right, so we've got 2 coulombs going through this resistor per second and 4 coulombs going through this resistor per second. All right, so in this wire here, we've got 4 coulombs per second. 1, 2, 3, 4. All right, and right here, we've got the 2 coulombs going, that everybody's going back to the battery. And once they get to this section of wire here, we're back to 6 coulombs per second going through this section here. All right, and those coulombs go back to the battery, and around they go again. We'll do it one more time. All right, we had 4 coulombs going to this resistor. We had the 2 coulombs going to this resistor. All right, taking a quick right and swinging through this resistor. Okay, so we had a current of 4 coulombs per second going through this resistor and 2 coulombs per second going through this resistor. When they get to here, they head back to the battery. All right, when these guys get to here, okay, again, we're all heading back to the battery. Zip, okay, and in this part of the wire right here, we're back to a current of 6 coulombs per second. All right, so right away you see a big difference when it comes to current between a series circuit and a parallel circuit. In the series circuit, the 6 coulombs had no place else to go. There were no choices about what direction to take. So if 6 coulombs per second came out of the battery, 6 coulombs per second went through the first resistor, 6 coulombs per second went through the second resistor. In the parallel circuit, when the 6 coulombs per second get to here, there's a choice. They're going to split up somehow. It could be 3 and 3, it could be 2 and 4, it could be 1.5 and 4.5. All right, that's going to depend on some other things that we're not going to go into detail about right now. But in any case, the current going through all the different resistors does not have to be the same. Right? And it's not the same as the current when it comes out of the battery.